Hello, everyone, and welcome back. We are at the very last concept of Chapter 7 and getting towards the end of this curriculum, where this section, Chapter 7.3, is all going to be about differential equations. Okay, so let's recall what we've been doing in the past in this year is if we were given a function, say y equals x squared, what we were able to do is that we could differentiate each side, and we would say that dy dx is equal to 2x, right? And again, remember that dy dx, this represents, the rate of change, and not even the rate of change, the instantaneous rate of change, instant rate of change of the function y equals x squared. Now, this is a differential equation, right? This is called a differential equation. Differential equation. But that word differential is talking about like taking the derivative of something, and that's what we always use, differentiate the function was always saying find the derivative of this function. So given a function y equals x squared, we were able to get the derivative to be 2x. All right, and then visually, to show you this, before we look at what's going to be happening, just to give you a little bit of background in this chapter. And so if we had the function y equals x squared, which I'll do in this pen here, look, a sketch of it would look something like this. There's y. Well, if you were to graph the slope function 2x, starting at 0 up 2 over 1, it would look something like this, where this function defines its slope at any moment. Right? Now, where are we heading this chapter is, let me finish making that look good, is in the past it was given y, what's the derivative? Now, what we're going to be studying instead is instead of focusing on the function y, we're going to focus on the differential equation from the beginning. So now the idea is we're going to be given dy dx. And say, for example, dy dx is equal to 2x. Okay. Now the idea is then, given this, what's your function y? Okay. And that's the big change, and that's what this whole section is going to be about. In fact, if you go on to study math in college right now, differential equations are one of the biggest fields in calculus right now, with a lot to be explored still. Now, we're just learning about it, but if you were to study it, these can get pretty complex pretty quick, and I'll show you that in a second. So take a look at this problem. If I give it visually, like I did just previously, is now the idea is if we're given 2x, I'll stick with it in green, so up 2 over 1, etc. All right, so there's your dy dx, your differential equation. So again, that's called your differential equation, talking about how something is changing. Well, what's y? Right? Now you might think that it's just going to be y equals x squared, but you're going to see in a second right here, it doesn't, this is just one possible solution. In fact, you're going to see in a second that there are a lot of answers we could get here, in which you might be saying, what are you doing, Ms. Shine? And I'll talk about that in just a second. All right. Any one of these can be y. Which one is it? Right. You might be even saying, why are you even doing that? Well, let's explore, okay? So this video is going to talk about solving differential equations. So let's look at 3 examples. All right. So solving differentials. Differential equations, which again, that's your dy dx or your y prime, depending. Just recognize both formats there, okay? Get rid of that. Example 1. Let's do dy dx equals 2x. The problem that I just left off with, so we can make sense of that visual. All right, so we're going to solve for y. So what we're going to do is you're going to multiply dx to both sides and write dy equals 2x dx. All right? Kind of the idea that you're separating the variables in a way. So make a little note. It's like the separation of variables. Okay. From here, if we want y, we're going to integrate both sides. Now the idea here is you're integrating dy with respect to y, which will just give you y plus some constant c, remember, because it's an open interval. And I'm putting c1, and I'll explain why in a second. Well, over here, if you integrate 2x, now you're integrating this with respect to x, you'll get 2, and then you'll get x squared over 2 plus some constant, which I'll call c2. And I say constant because, again, we don't know what those are. There can be infinitely many reasons. Maybe these are the same, maybe they aren't. Who knows? All right. Now, simplifying this up a bit, would have y plus c1 is equal to x squared plus c2. And now this is the kind of the new part here, is if you were to just combine the constants on one side, we're going to get y equals x squared. Now, if you minus a constant number, since we don't know what these are, we just know that we can combine the numbers, we're going to get some sort of number. So we're just going to put plus one constant c. So instead of keeping constants on both sides, the idea is if you move this one over, if you minus c1 from this side, it's just going to result in some constant c, which is just some constant. And there is your answer. So notice, given your differential equation of 2x, what function is this representing the rate of change of? It's representing the rate of change of the function x squared plus some vertical shift. Now this explains why we got the graph up here. Because the idea is that we're given the slope 2x. Now what's that talking about? It's the rate of what function? It's the rate of which one? Because again, the idea is that what we got is x squared plus c. Because there can be infinitely many functions that follow this rate of change. All right. Now, it's important with these, and we check our answers. So let's check to make sure we did this right. So let's take the derivative with respect to x of this function and make sure that we got, does this equal 2x is what we're checking. All right, I'll make sure that we get the original problem. So then you'll get dy dx is equal to 2x, and the derivative of c is 0, so that is in fact 2x. Good. All right, let's look at another example, example 2. All right, we're going to do dy dx is equal to y. All right. Now, we mentioned when we first looked at circles, I think when we first looked at circles and we found the slope of a tangent line was the first time with implicit differentiation we got in terms of y. So now let's look at this. Now, how do we do this? So kind of like how earlier we had to separate the variables, you have to do the same thing here, where I might times the dx over and get y dx. But again, I need y's on both sides if I'm going to integrate with respect to that variable. So then I'm going to divide both sides by y and get dy over y equals dx. And now that they're separated in that regard, you can integrate both sides. So integrating this side with respect to y. So what's the antiderivative of 1 over y? Well, that's the natural log of the absolute value of y. And I'll put plus some constant c is equal to, now it's the integral of dx, which remember is like a 1 dx. There's a 1 in front there. So the integral of 1 is just x plus some constant c. And really, as I move forward in these videos, I'm not going to put the plus c on the left side. I'll pretty much just be putting on the right side only, with the idea that I'm going to skip that step. So hopefully you see that. Now, how do we solve for y from here is, now we can rewrite this in exponential form, where you can write that as e to the x plus c equals the absolute value of y. And then that we can write as y equals, now absolute value means plus or minus, so I'm going to count for that on the other side, plus or minus e to the x plus c. And this is the trick here with some algebra, is remember, when exponents are adding, we can actually split that up by keeping the same base, but multiplying them. All right, so for example, up here, remember that x, say x to the 5th, is the same as x to the 3rd times x squared, where you can separate them by addition. So that addition, we can separate them. Well, what's e to the c? Remember that e to the c, well, this is just some number. And the fact that c can be anything, this e to the c can really be any number. Now, it probably would be, well, it'll be any number, and the positive negative will account for it being positive or negative. So your final answer here is actually, we're going to make all that c, because it's just some number, plus or minus e to the x. And there's your answer to that differential equation. All right. Now, let's check our answer, and then we'll look at one more after this. Let's check and make sure we did this right. What's the derivative with respect to x of y equals c e to the x? Okay, so then we'll get dy dx is equal to, Now, the c I can pull out, so I'm going to do c times the derivative of e to the x, because c is just a constant again. So what I'll get is dy dx is equal to c, and then what's the derivative of e dx? Well, that's e to the x. And then notice that ce to the x from this original step is equal to y. So thus dy dx is equal to y. And there's your check right there. Okay. Good. And let's look at one more, and then we will wrap this up. So, example 3, last one, is given the differential equation dy dx is equal to y squared. What's the original function y? Now, do notice what's interesting in the last one is notice that the antiderivative was ce to the x, plus or minus depending what that constant is. In this case, it's that's the best way I can say this. Your antiderivative is a stretch factor rather than a vertical shift, which you'll see in the coming sections, but I just want to make sure you're aware of where that constant shows up. So when it was in terms of x, it was a plus c. Now that's in terms of y, notice that's a times c. Okay, something to take note of. All right, anyway, example 3, dy dx equals y squared. So we're going to separate the variables. Right, this is y squared dx, and then divide by y squared to both sides. Then we can integrate both sides with respect to their variable. So integrating with respect to y, remember that this I might rewrite as y to the -2 dy, just to help you see this, and maybe I do 1 dx as we're learning this. Antiderivative of -2 would be you add 1, so it'd be y to the -1 over -1. And I'm not going to put the plus c because you've seen it already. I just got the plus c on the right side there. So I can write this as -1 over y equals x plus c. And then let's see here. If I solve for y now, say I put this over 1 and I cross multiply, I'll have it y times x plus c equals -1. And then dividing that over, we'll have y equals -1 over x plus some constant c. And there you go. Okay, and let's check. Make sure we did that one right. So let's check. If we take the derivative of this solution here, which again, that plus c, remember that means that there's infinitely many functions that have a rate of change of y squared. Right, so just keep that in mind. So let's check. So the derivative of this is going to be dy dx is equal to, now this is -1 over x plus c, so it's going to be negative. And then since it's x plus c, it's going to be the natural log of x plus c. Okay. And let's see, how can we check this one? The derivative of that is -1 over x plus c. Now is this, and we're trying to get y squared. Oh, I caught my mistake. You're probably like, dang, did the video freeze? It didn't. This is not true. That's the integral of -1 over x plus c, not the derivative. My brain eluded me for a second. So let's fix that really quick. So let's go dy dx. It's going to equal, so it's the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, which would just be 1, all over the bottom squared. So then we'll get dy dx is equal to, that just makes 1 on top, over x plus c squared. Well, notice that we can rewrite this as 1 over x plus c times 1 over x plus c. And 1 over x plus c is y, well, the negative version of it. So what we're going to get here is -y times another -y, which is equal to y squared. And thus, we got our same answer. Very good. So there it is, solving differentials. The idea is going back to the beginning, and maybe pause the video if I went too quick, but in the past, it's given a function y, let's talk about its rate, but now it's given a rate function, let's talk about what it represents the rate of, in which case we're going to be getting infinitely many answers. And you just have to remember the idea to separate the variables before you integrate. Okay. Hope that helps, and I hope you can try it yourself and make sense of these yourself a little bit more. All right. Take care. Bye-bye.